Okay, so we're going to do another exam style question on waves. A baby monitor has a sensor unit that transmits an image of the baby and the noises the baby makes into a monitor unit. The monitor then displays an image of the baby and emits the noises the baby makes. Compare the properties of the waves that transmit images and noises from the monitor unit. Okay, so we have a sensor unit which picks up visible light coming off the baby and also sound. Then it sends this information to a monitor unit which then displays an image of the baby by releasing light waves and also emits the noises the baby makes via sound waves. The question is saying compare the property of the waves that are released. In other words, compare the properties of light versus sound. Okay, so light waves are an example of a transverse wave. In fact, all electromagnetic waves, micro, radio, infrared, visible light, ultraviolet, X-ray and gamma ray, they are all transverse waves. Sound, on the other hand, is a longitudinal wave. So that's 1 mark. Okay, let's see if we can get 4. In transverse waves, the oscillations or the vibrations are perpendicular to the wave, whereas in a longitudinal wave, such as sound, the oscillations are parallel. 2 marks. Light waves are much more faster than sound. We all know this from the example of thunder and lightning. We see the lightning first, we see the flash, and then we hear it later. So light travels faster than sound. Light waves also have a higher frequency than sound waves. Okay, so that's 4 differences, but let's see if we can get any more. Another difference is that light has a much shorter wavelength than sound. And finally, light, because it's an electromagnetic wave, can travel in a vacuum. Sound, however, requires a medium. Okay, moving on to the next question. The sensor unit can detect infrared and visible light. So just one advantage of being able to detect infrared. So we said that the sensor picks up visible light from the baby. Then it sends this information to the monitor unit. What would happen then if it was in a dark room? Does that mean we can't see the baby? Well, the sensor can still pick up infrared radiation. Remember, all living things release infrared radiation, or in other words, heat. This will be picked up by the sensor and sent to the monitor, and again, we can produce the image of the baby. So one advantage is that we can see the baby even if it's in a dark room. Write down the equation that links frequency, wave speed, and wavelength. So this is a very popular equation that we all have to know, which is speed equals frequency times wavelength. These are the symbols that we can often see. For speed is V, frequency is F, and wavelength is this weird little symbol called lambda. And these are the units. So meters per second for speed, hertz for frequency, and meters for wavelength. Part D. The signal from the monitor units are transmitted as electromagnetic waves with a wavelength of 0.125 meters. The wave speed is equal to 3 times 10 to the power of 8 meters per second. So basically a very big number. Or in other words, 300 million meters per second. That's how fast light travels. Calculate the frequency of the signal. So we've been given wavelength and wave speed, and we want to work out frequency. So we're going to use the equation speed equals frequency times wavelength, and that gives us the following. Then we're going to rearrange to find frequency. So speed over wavelength, and we get the following answer, 2.4 times 10 to the power of 9 hertz. Here's another exam style question on waves. A note was played on an electric keyboard and the frequency was 440 hertz. What does a frequency of 440 hertz mean? So 1 hertz is equal to 1 wave per second. Therefore, 440 hertz is equal to 440 waves per second. Part 2. The sound waves has a speed of. Calculate the wavelength. Again, we're going to use the same equation, speed equals frequency times wavelength. This time, however, we want to work out wavelength. So we're going to rearrange and then plug in the values that we've been given. The speed was 340 meters per second and the frequency was 440 hertz. That gives us a final answer of 0.773 meters. part B. The figure shows a microphone connected to a CRO, and it's being used to detect the note produced by the keyboard. Figure 2 shows the trace produced by the sound wave on the CRO. So we can see here that a sound was played on the keyboard, and this was detected by the microphone, and on the CRO we got the following diagram. A second note of different wavelength was played on the keyboard. Figure 3 shows the trace produced by the sound wave of the second note. And this is figure 3. So we can see now that we have a different trace. What two conclusions can be made about the second sound wave produced? Okay, so if we compare these two, first of all, the height of a wave is also known as the amplitude, and this measures loudness. We can see here that the two waves have different amplitudes. Figure 3, or the second wave, has a much higher sound wave. So therefore, it must be louder. And the reason is because the amplitude is larger. Now, the number of waves is equal to frequency, and this measures the pitch of a sound. So if we look at the second diagram, we have 1, 2, 3, 4 waves. And in the second one, we had 1, 2, and a half. So 2.5 waves. Therefore, figure 3 must have a higher pitch. And the reason is because more waves are seen on the CRO. Hey guys, if that video helped you, support our channel by liking, subscribing, and sharing it with your friends. And more importantly, if you still have questions, drop a post on our forum at ExamQA.com, where I will personally be there to help answer your questions. Mohammed signing out.